Hello children, welcome to online classes. We started P block in the last class. In the last class, we have learned 15th group elements, their general properties, hydrides as well as preparation properties of dinitrogen. In the last class, we learned general properties of the 15th group elements, hydrides, their properties, as well as preparation and properties of dinitrogen. In today's class, we are going to learn the oxides of nitrogen, structure of oxides of nitrogen, preparation and properties of ammonia, and preparation properties of nitric acid. In today's class, we are going to learn oxides of nitrogen and the structure of oxides of nitrogen, preparation properties of ammonia, preparation and the properties of nitric acid. Let us now see the structure of oxides of nitrogen. Let us take the first compound N2O, which is called nitrous oxide N2O. So take structure in this way, that is N2. We know the structure of N2. So N2 structure having two lone pairs on each N is having one lone pair, and right here one oxygen atom here having 6 valence electrons here, and this make it a coordinate covalent bond from nitrogen to oxygen. So this pair will be a coordinate covalent bond for us now. Means nitrogen, triple bond, nitrogen. We have a coordinate covalent bond towards oxygen, having here 3 pairs upon oxygen. We have a lone pair on this one now. This is the structure of N2O molecule. When you are drawing resonance structure of N2O molecule, shift this pair of electrons between these two atoms and then shift this one to this nitrogen atom. Means nitrogen, we get only double bond here, nitrogen, and another double bond towards oxygen atom. Now oxygen is left only with 2 pairs of electrons here, and nitrogen has one extra lone pair of electron. So between these two, means these two are the resonating structures of nitric oxide. When it comes to bond length, N bond length will be equal to 1.13 angstrom units, and NO bond length is coming to 1.19 angstrom units we have. Structure will be linear as well as diamagnetic in nature. Linear and diamagnetic in nature. So bond lengths of N and NO are different here, and these two are the resonating structures of nitrous oxide. Means we write first of all N2 and put a bond, that is coordinate covalent bond towards the oxygen. Then we can get the corresponding structure, that is a nitrous oxide structure. The next molecule is NO, that is nitric oxide. So N double bond O, nitric oxide here. And oxygen will be having totally 6 valence electrons. So 1, 2, 3, 4, 5 and 6 we have. A nitrogen has 5 valence electrons. So 1, 2, 3, 4 and 5. So fifth is going to be odd electron for nitrogen atom. Or it can have the structure other way also. Means oxygen will be having odd electron on that. In that case, nitrogen gets even electrons here, double bond here, and then oxygen is going to have odd electron then now. It will be resonating structures between these two. Means NO we can say finally, NO we have. So here NO will be an odd electron molecule now, odd electron molecule, therefore paramagnetic in nature, and bond length is 1.15 angstrom units or 115 pm we can say. In gaseous state, but when it comes to solid or liquid state, it dimerizes and becomes there diamagnetic in nature. So in the gaseous phase, it is odd electron, because odd electron may be on nitrogen atom, it can be even on the oxygen atom. So odd electron species we have. When it comes to in the liquid state or else in the solid state dimerizes, then you can see structure of this form. So nitrogen here, oxygen here, nitrogen. This type of structure exists in the solid state or liquid state. This is going to be diamagnetic in nature now. And this molecule is going to be paramagnetic in nature. This is the structure of nitric oxide. So odd electron will be in the gaseous form. Then next, NO2 molecule, nitrogen dioxide molecule. So here's some simple structure here. So nitrogen, we have one double bond oxygen atom. So with this, nitrogen utilizing 2 electrons here now. And then one coordinate covalent bond towards oxygen atom here. Means N is using another pair of electrons here now. So 4 are being used and therefore 1 is left upon nitrogen atom. Odd electron species upon nitrogen atom. Once again the molecule can have two resonating structures. Means let us draw this molecule in this form. So N nitrogen. So we have double bond O. We have a coordinate covalent bond with oxygen atom here. And then odd electron present here now. So two forms we can write finally in this way. Nitrogen, double bond, single bond here, resonance with nitrogen, single bond, and then double bond here, both having odd electron on that. These two are resonating structures. So bond lengths will be equal now because of resonance structure. So bond length is coming up to 1.20 angstrom units. Bond angle is 134 degrees. Molecule is angular molecule, and then paramagnetic property, because of the presence of here odd electron is there, therefore the molecule is paramagnetic in nature. So we have a one coordinate covalent bond, we have a double bond with another oxygen atom. This is structure of nitrogen dioxide. Then comes nitrogen trioxide. This can be taken as summation of nitric oxide plus nitrogen dioxide, because NO as well as NO2, NO and NO2 both have odd electrons on nitrogen atom. They are now getting paired up to form N2O3. Let us take NO2. So NO2 is having one double bond. Just now we have seen we have one coordinate covalent bond towards oxygen atom here. So the coordinate covalent bond means we have 3 pairs here. This has only 2 pairs here. And then odd electron here. The nitrogen having a double bond here. This oxygen is having 2 lone pairs here. Means you are going to get one odd electron that is present here now. So these two are being bonded here. And then these two bond, this side the bonds again will be in resonance here structure. Thereby this side bond lengths are going to be equal. Means we can draw another resonating structure for this. So nitrogen, here we can take single bond this side and then double bond here. One bond here, nitrogen, and then oxygen here now. Nitrogen is having a pair of electrons here now. So this oxygen is having 1, 2, 3, 4, 5, 6 are there. This has 2 pairs of electrons. So the bond length on this side remains the same now. That bond length is coming to 1.21 angstrom units we have. This side bond length, this side bond lengths are not same. 1.14 angstrom units is 1.14 angstrom units we have. This side the bond length is 1.21 angstrom units we have. Both the bond lengths are not same. NN bond length is given as 1.86, means this bond length is given as there 1.86 angstrom units. And bond angles 130, this side you have 130 degrees is there now. And this side, this is not a linear structure. This side angle is found to be 105 degrees. So remember that this side both bond lengths are same now. And this NO bond length on this side here and this side here, remember these two bond lengths, they are not same. But this side both the bond lengths are same. So imagine the structure of NO plus NO2 together will be N2O3 molecule. Then comes N2O4 structure. It's simply taken as dimer of NO2 itself now. So NO2 will have an odd electron. So take double bond O, one coordinate covalent bond, and one more nitrogen here now. Similarly, another NO2 molecule, coordinate covalent bond O, double bond O, we have odd electron here. Between these two, a bond is being formed. Is also having resonating structures here, that these two bonds will be equal now. Implies that nitrogen, it is single bond here and a multiple bond here, and here multiple bond here and a bond here now. So therefore all NO bond lengths are same. because of resonance structure. So all bond lengths are, NO bond lengths are 1.12 angstrom units. They are 1.21 angstrom units we have, 1.21 angstrom units. And then bond length is 1.75 angstrom units we have. This is regarding the bond lengths. So N2O4 is nothing but dimer of NO2 we have. So NO2 will be odd electron and paramagnetic in nature because of odd electron here now. When it comes to this, nothing but dimerizing. So therefore, it will be a diamagnetic in nature. N2O4 comes out to be a diamagnetic molecule. Then coming towards N2O5 molecule, this can be considered to be two NO2 units joined together through one oxygen atom. So this is one NO2 unit you have, one NO2 here and one NO2 unit here. Two units of NO2 are there joined through one oxygen atom. So we have one oxygen atom. Both sides we have NO2 units, means nitrogen here. We have one double bond O and a coordinate covalent bond O. Similarly, one nitrogen here, one coordinate covalent bond O and a multiple bond here now. This can be taken structure of this type. Again, we have resonating structures where these two bond lengths, means NO, this NO bond lengths are equal because of resonating structures. So this NO bond length and this NO bond length, these two are not same. You can see the bond lengths which are present there now. The NO bond length is 1.19 angstroms. This bond length is 1.19 angstroms we have. This is a 1.19 angstroms we have. But this NO bond length is 1.51 angstroms we have. 1.51 angstrom units we have. So bond lengths are not same. NO bond lengths on either side they are same, but not NON bond lengths are not same as NO bond lengths. Regarding structure of N2O5 molecule. These are the structures. Now let us see the preparation methods of these oxides now. First one, let us take nitrogen oxide, nothing but it is a N2O nitrous oxide, prepared by simple reaction by heating ammonium nitrate. So NH4NO3 ammonium nitrate on heating uses nitrous oxide. So by heating ammonium nitrate, we can get the compound N2O. When it comes to preparation of nitric oxide, it's prepared by heating a mixture of NaNO2, that is sodium nitrite plus ferrous sulfate plus H2SO4. By heating a mixture of these three compounds, sodium nitrite, ferrous sulfate and sulfuric acid, the products formed are, it will be ferric sulfate plus sodium bisulfate plus we get nitric oxide and then water. So by heating a mixture of sodium nitrite, ferrous sulfate, sulfuric acid, we get nitric oxide plus other products are ferric sulfate, sodium bisulfate. I am not balancing the equations here. I am just writing the main products and reactants here. So nitrous oxide is obtained by heating ammonium nitrate here. Nitric oxide is obtained by heating a mixture of NaNO2, ferrous sulfate and sulfuric acid. Let us take next one. Nitrogen dioxide, that is a NO2 we have. It is prepared by heating lead nitrate salt. So PbNO3 taken twice. So lead nitrate on heating gives lead oxide plus nitrogen dioxide plus it forms oxygen also. So lead nitrate on heating gives NO2 gas, PbO plus O2 are the byproducts for us now. Now let us take nitrogen trioxide, N2O3. So this can be taken as a mixture of NO2 and then NO. So therefore cooling equimolar mixture of nitrogen dioxide having odd electron here and then nitric oxide, cooling equimolar mixture, the temperature must be below 253 Kelvin. So by cooling equimolar mixture of NO2, we are going to get N2O3 molecule. So cooling equimolar mixture of NO and NO2. We get N2O3. Next one. Preparation of nitrogen tetroxide. It's simply a dimer. It is simply a dimer of NO2 itself. Nitrogen tetroxide, that is N2O4. So when you are cooling a mixture of say NO2, we cool a mixture of NO2, upon cooling itself you are going to get N2O4. And if you are heating N2O4, then you are going to get, if you heat this one, you are going to get NO2 molecule. Simply a dimer of NO2 itself is nitrogen tetroxide. Now coming towards nitrogen pentoxide. Nitrogen pentoxide is prepared by dehydration of HNO3. HNO3 on dehydration using phosphorus pentoxide as a dehydrating reagent gives rise to N2O5. It forms N2O5 and byproduct is HPO3, that is metaphosphoric acid we have. So dehydration of HNO3 itself gives rise to N2O5. These are the preparations of oxides of nitrogen. Let us see the summary here now. So first one, the dinitrogen oxide, that is nitrous oxide, nitrogen state is equal to +1 here, is prepared by heating ammonium nitrate, use nitrous oxide plus water, and it is a colorless gas, neutral compound. First two of them are neutral in nature and others are acidic in nature. Second molecule is nitrogen oxide, nothing but monoxide we can say, or nitric oxide also, prepared by heating a mixture of heating a mixture of sodium nitrite, ferrous sulfate and sulfuric acid. We get NO, others are byproducts. Is also a colorless gas and neutral in nature. Preparation of N2O3, prepared by cooling equimolar mixture of NO and then N2O4. Actually N2O4 is a dimer of NO2 only. We get there N2O3. Then comes nitrogen dioxide, prepared by heating lead nitrate salt. It gives NO2 and other products are PbO and O2 we have. N2O4 is only a dimer of NO2. So NO2 on dimerization you are going to get N2O4. On cooling we heat it, we get back NO2 molecule. And finally nitrogen pentoxide is obtained by dehydration of, it is HNO3, using phosphorus pentoxide as a dehydrating reagent. We get there N2O5 plus HPO3. It is a colorless solid and acidic in nature. We have colorless solid and acidic nature. And then coming towards N2O4 molecule, it is a colorless liquid. We have colorless liquid and acidic in nature. These are the preparation methods of oxides of nitrogen. Then comes preparation of ammonia. Ammonia is prepared by decay of nitrogenous organic matter. Nitrogenous organic matter, something like urea. Urea actually in the presence of an enzyme called urease. It decomposes to ammonia and carbon dioxide now. When ammonia and carbon dioxide are there, this will be again equilibrium with ammonium carbonate. So urea, the presence of enzyme urease that decomposes to ammonia and carbon dioxide, these two in turn will be in equilibrium with ammonium carbonate. So it is a nitrogenous organic matter. Decay also gives rise to ammonia. Now in the laboratory process, any ammonium salt with a caustic soda, or else it can be calcium hydroxide, use ammonia gas. Any ammonium salt we can take and add there. So any base that can be added to that. So sodium sulfate, some ammonium salt plus NaOH. Use ammonia and sodium sulfate here now. Ammonium sulfate plus sodium hydroxide, use ammonia plus sodium sulfate. You can take even ammonium chloride also, add for this calcium hydroxide a base, then also you are going to get ammonia gas. So in general, you can take any ammonium salt and add a base, we are going to get ammonia gas. For that we have taken two examples. One is ammonium sulfate, addition of NaOH. Other one is ammonium chloride, addition of calcium hydroxide we have. Then comes commercial preparation method, which is done by a process called Haber's process, where we can prepare ammonia in large scale method. And the reaction is simple. Directly from elements, ammonia can be prepared. Reaction is coming under exothermic in nature now. And coming towards the optimum conditions to be maintained here now, temperature of about 700 to 750 Kelvin is maintained, and high pressure of about 200 atmospheres, and finely divided ion is acting as a catalyst here now, and promoter is molybdenum or oxides of, you can say, potassium or aluminum. These conditions actually can be known by Le-Chatelier's principle, which we discussed in the first year itself now. So optimum temperature, optimum pressure, and a catalyst are being used in the preparation, the Haber's process. Let us see the process now. So the process consists of, let us see the process here. So a mixture of N2 and H2 in the ratio 1 is to 3, the ratio 1 is to 3 is being passed into compressor first, being passed into compressor. This gas mixture here, this gas mixture here is compressed to a pressure of 200 to 900 atmospheres. That is, by means of a compressor, gas mixture is compressed. The compressed gases are then passed into catalytic chamber. From here, the gas mixture is being passed into catalytic chamber. There, they are being passed into catalytic chamber. The catalytic chamber contains finely divided iron at a temperature of about 700 Kelvin. You have it is having iron at a temperature of about 700 Kelvin, and here actual reaction takes place between N2 and then H2. So we are passing gases mixture into compressor first. Gas are compressed to high pressure, and then the compressed gas mixture is being passed into catalytic chamber. There you have a catalyst at a temperature of about 700 Kelvin. Here actual reaction takes place between N2 and then H2, means ammonia is being formed. Once ammonia is being formed here, this is being passed into condenser. Ammonia is being passed into condenser so that ammonia gets liquefied. Liquid ammonia can be collected. Then the unreacted N2 and then H2 which are left, again they are passed into the compressor, with the help of a recirculating pump. The unreacted N2 and H2 are passed into the compressor, and in this way the whole process again repeated. In this way ammonia can be prepared. Let us see once again. So a mixture of N2 and H2 are passed first of all into compressor, where they are compressed to high pressure of about 200 to 900 atmospheres. From this they are passed into catalytic chamber, where you have a catalyst at high temperature of about 700 Kelvin. Here actual reaction takes place between nitrogen and then hydrogen. Formation of ammonia takes place here. From catalytic chamber, ammonia is being passed into condenser. There ammonia is being condensed to the liquid, and liquid ammonia can be collected now. And in the entire process, there may be some unreacted H2 and N2 left, that is again being passed back again into compressor with the help of a recirculating pump. In this way, ammonia is prepared in the large scale process. Now coming towards properties of ammonia. Ammonia is a colorless gas with pungent smell. So freezing point is 198.4 Kelvin and boiling point is 239.7. It's having a higher boiling point when compared to other hydrates in that group. That is because of intermolecular hydrogen bonding. Ammonia has higher boiling point because of intermolecular hydrogen bonding. Ammonia is highly soluble in water, again because of hydrogen bonding only, and its aqueous solution is weakly basic. It contains OH minus ions in that. When H4OH is there, it forms again OH minus ion. So ammonia is colorless gas having pungent smell, has a higher boiling point because of intermolecular hydrogen bonding. It is highly soluble in water and is very weakly basic in nature. In the presence of OH minus ions are there in that. Coming towards structure of ammonia, as we all know from chemical bonding chapter, in ammonia nitrogen undergoes sp3 hybridization. It has 3 bond pairs and a lone pair of electrons. Therefore ammonia is coming under pyramidal shape and bond angle is 107 degrees we have. So nitrogen undergoes sp3 hybridization and it is having 3 bond pairs and 1 lone pair. Structure is pyramidal shape we have, and then bond angle is 107 degrees. Now coming towards chemical properties of ammonia. reactions with aqueous solution, aqueous ammonia solution, if you see now, that is, many metal salt solutions form their hydroxides as precipitates. Let us take some metal salts, say like CrCl3 metal salt with ammonium hydroxide, means aqueous ammonia solution contains ammonium hydroxide. This gives rise to CrOH taken thrice. It forms chromic hydroxide, is a precipitation here, plus byproduct will be ammonium chloride, NH4Cl. And this is green color precipitation. This is green PPT. Suppose when you take ferric chloride plus ammonium hydroxide here, NH4OH, ammonium hydroxide. This forms ferric hydroxide precipitation, FeOH taken thrice, precipitation plus byproduct remains same, ammonium chloride. And here the color is red, we have red color precipitation we can see now. In this way, some metal salt solution will form their hydroxide as precipitates now. These reactions are basically used in the salt analysis also. Now, in some cases, the precipitates dissolve in excess of ammonia because of the complex formation. In some cases only, the precipitate dissolve in excess of ammonia due to the complex formation. Let us take, for example, copper sulfate is there. So, copper sulfate plus ammonium hydroxide. So, it forms copper hydroxide. Copper hydroxide is being formed here plus ammonium sulfate. Now, when you add excess of ammonium hydroxide to the entire mixture, means you have copper hydroxide as a precipitate plus we have already ammonium sulfate there. Further add here ammonium hydroxide, means you are using here excess of aqueous ammonia there. Then you are going to get a complex now, which is copper tetraamine complex formation takes place plus water. This is a tetraamine copper sulfate. This is tetraamine copper sulfate. It is water soluble one. So when you take excess of ammonia, the precipitate formed is dissolves in the case of copper sulfate. Similarly, we can take reaction, you can take even say zinc sulfate also, zinc sulfate plus let us take aqueous ammonia. This forms again here also, it forms a complexation there. This forms tetraamine zinc is being formed in this case. Is also soluble one, complex, but it will be water soluble one. Now AgCl is actually a precipitate, it's a solid here. When you take here aqueous ammonia, this also dissolves due to the formation of complex. Silver diamine complex formation takes place in this case. So in some cases, when you are using excess of ammonia, the precipitate formed will be soluble there now. This is regarding chemical properties of the ammonia. Then use of ammonia in the manufacturing process of nitrogenous fertilizers like urea, the ammonia can be used. The preparation of ammonium nitrate, ammonium sulfate, etc., ammonia is used. And ammonia in the form of liquid ammonia is used as a refrigerant. Liquid ammonia is basically used as a refrigerant. So ammonia used in the nitrogenous fertilizers like urea, ammonium nitrate, ammonium sulfate, etc. Liquid ammonia can be used as a refrigerant. With this ammonia we have done. Next one, the oxo acids of nitrogen. Nitrogen mainly forms 4 oxo acids, that is a hyponitrous acid, that is you can take it as HNO but taken twice, so H2N2O2, nitrous acid HNO2, nitric acid HNO3, and pernitric acid HNO4. Pernitric acid has a peroxy bond in this one. So we are familiar with these two acids, that is the nitrous as well as nitric acids. Remaining two we need to learn now. That is the same hyponitrous acid H2N2O2, nitrous acid nitric acid and pernitric acid. In the oxides of nitrogen, all of them are monobasic in nature. All are monobasic. Implies that all of them will have one OH group bonded to nitrogen. All are monobasic, so it's having one OH group bonded to nitrogen. And nitrogen also has one double bond towards oxygen. Also, it's having one double bond towards oxygen. So these two are present in all oxyacids of nitrogen except the case of H2N2O2. So it's a monobasic in nature. Thereby, in all oxyacids of nitrogen, we have one NOH group, we have one N double bond O is there, except in the case of hyponitrous acid. Let us now see the structures of these molecules now. So hyponitrous acid here. The basicity is 2 only for this one. Here N2 and there are 2 OH groups here now. So one OH group like this, other can be taken like this now. Because of double bond present here, it has 2 different forms also. Anti and syn structures are there. We can have one more form of this type. Isomers. Anti and syn type of structures. So H2N2O2 is called hyponitrous acid and its basicity is 2 because there are 2 OH groups now. HNO2 nitrous acid. So let us follow general principle. There should be one OH group, one doubly bonded oxygen atom. So nitrogen, we have one OH group here and there should be one doubly bonded oxygen atom present. That implies nitrogen has another lone pair which is present here now. So this is going to be structure of HNO2. The next one now. It is a monobasic because of only one OH group. HNO3, that is to say nitric acid structure. Nitric acid structure here, let us follow the normal principle here. Nitrogen having one OH group here and then one double bond O is there. Still we have a pair of electrons present in a nitrogen atom. They are going to form one coordinate covalent bond towards another oxygen atom. Because nitrogen can form only 4 bonds to maximum extent. It can form only 4 bonds. It cannot form one more multiple bond towards oxygen atom. It is going to be a coordinate covalent bond. HNO3, one OH group. Then pernitric acid. So nitrogen again here. It is having a peroxy bond. Therefore, we have one O bond that is present here. Peroxy bond is there. One double bond O. And again we have a coordinate covalent bond towards another oxygen atom. These are the structures of oxyacids of nitrogen. So if you see the first one, H2N2O2, N2 and put 2H groups on both sides now. HNO2, remember in all oxyacids, nitrogen has one OH group and one doubly bonded oxygen we have. So HNO2. HNO3, nitrogen, one OH group, one double bond oxygen is there. Still we have one more oxygen left in the formula. So put coordinate covalent bond. And per nitric acid has a peroxy bond in that. So it is having OO group in that. OOH is there. So again OO group here, one double bonded oxygen atom and one coordinate covalent bond we have. This is regarding the structures of oxyacids of nitrogen. Then nitric acid preparation we have. It is prepared in the laboratory by reacting nitrate salts with sulfuric acid. So nitrate salt with sulfuric acid gives rise to HNO3 and byproduct is in this case sodium bisulfate. If you are using their potassium nitrate, you are going to get HNO3 as well as the byproduct will be potassium bisulfate. So in the laboratory they are prepared directly by the action of concentrated sulfuric acid on nitrate salts. Then comes large scale preparation. It's done by Ostwald's process. The principal reactions are as follows. Here ammonia is catalytically oxidized to nitric oxide. So ammonia plus oxygen gas is oxidized to nitric oxide with the help of a platinum catalyst or platinum catalyst is used here. 9 atmospheres pressure, nearly 9 bar you can say, and 500 Kelvin. So catalytically it is being oxidized to nitric oxide here. And nitric oxide is further oxidized to nitrogen dioxide. So NO plus O2 gives rise to NO2 there. NO2 is now dissolved in water to get finally HNO3. So ammonia is oxidized to nitric oxide. Nitric oxide is further oxidized to nitrogen dioxide that is finally dissolved in water to get HNO3. These are the principal reactions taking place. Let us now see the Ostwald's process. A mixture of dry ammonia and a purified oxygen, especially free from the dust, is being passed into catalytic chamber. The chamber contains platinum gauze, heated to a temperature of nearly 1100 Kelvin. We have heated to 1100 Kelvin now. Here, once it is heated, further it need not be heated because the heat of reaction itself is sufficient to maintain the temperature. So we are heating to 1100 Kelvin now. Heating to 1100 Kelvin, and in the catalytic chamber, ammonia is rapidly oxidized. Here, ammonia is rapidly oxidized to nitric oxide. The gases from catalytic converter are cooled and then mixed with air in the large empty chamber, which is called oxidation chamber. Here, NO gets oxidized further to nitrogen dioxide. NO is getting oxidized to nitrogen dioxide. The gases are then introduced into absorption tower, which contains stones, which contains quartz pieces or stones. We can say acid-proof stones are present. Acid-proof stones are present in the absorption tower. Water is sprayed from the top, which dissolves NO2 in the presence of oxygen gas. This gives finally HNO3 for us now. It gives finally HNO3. Let us see the process once again. So a mixture of 1 volume of ammonia and 8 volumes of oxygen, which is completely free from the dust, is passed into catalytic chamber, which contains platinum at 1100 Kelvin, and once it is heated, further we need not heat because the heat of reaction itself maintains the heat. Now, once NO is being formed here, means ammonia is getting oxidized to NO. Once NO is being formed here, it is now passed into oxidation chamber, where NO gets oxidized to nitrogen dioxide. The NO2 is now passed into absorption tower, which contains stones which are acid-proof, above which water is continuously sprayed now. In the water, NO2 dissolves, and finally you are going to get HNO3 that can be collected. This is regarding manufacturing process of HNO3 by Ostwald's process. Now let us see the structure and the properties of HNO3. It is a colorless liquid. Freezing point is 231.4 Kelvin and boiling point is 355.6 Kelvin we have. In the gaseous state, it is a planar molecule. In the gaseous state. A nitrogen atom in nitric acid undergoes sp2 hybridization. And structure already we have seen. The basicity is equal to 1. It is a monobasic in nature. That is, only one OH group is present in that. So, it's a colorless liquid planar molecule in the gaseous state. Hybridization is sp2. Basicity is only 1, means it is having only one OH group. Then, HNO3 is a strong oxidizing agent. It oxidizes metals to respect to metal nitrates, and the products formed other than metal nitrates depend upon the concentration of the acid, temperature, as well as nature of the metal. So HNO3 is a strong oxidizing agent. So all metals are oxidized to respect to metal nitrates here, and the products formed depend upon the concentration of the acid, temperature, as well as the nature of the metal used. Now, let us take different reactions now. It oxidizes non-metals also to corresponding oxo acids. Let us take, for example, sulfur. Sulfur will be oxidized to sulfuric acid, H2SO4. Reactions, say HNO3 gives H2O plus NO2 plus it forms nascent oxygen. The sulfur plus nascent oxygen plus H2O, they are going to give us sulfuric acid. Let us balance the complete reaction. The first one, here we require H2 is there, so 2 here and 2 NO2. First reaction. And coming towards second reaction here, one oxygen is there, 3 we require here 3 oxygen atoms, implies multiply the entire thing with 3 into 3 we have. Adding them, sulfur plus it will be 6 HNO3 giving rise to H2SO4 plus 6 NO2 plus H2O. 4 moles of H2O we have. Sulfur is getting oxidized to corresponding sulfuric acid. So initially sulfur changes into oxide here. That oxide dissolves in water and finally you are going to get sulfuric acid. So sulfur gets oxidized to sulfuric acid. Let us take now the example of phosphorus. Phosphorus gets oxidized to phosphoric acid. Reactions are same with HNO3. HNO3 gives rise to H2O plus NO2 plus nascent oxygen. Now the phosphorus plus nascent oxygen plus water, you are going to get their phosphoric acid, H3PO4. So upon balancing this, you are going to get 2 and 2 here now. When you are balancing the second reaction here, so this will be 3, this should be here 2 then now. This is now here we have 2. And oxygen will be 5 then now. So we require 5 oxygens, so this should be multiplied by 5 here. So into 5. So adding the both reactions, we get 2 phosphorus plus it will be 10 HNO3 giving rise to 2 moles of phosphoric acid plus 10 moles NO2 plus 2 moles H2O. 2 moles of H2O because we have this side 3 H2O is there, this side you are going to get 5 H2O. It will be 2 moles of H2O in this case. So phosphorus gets oxidized to phosphoric acid. You can take even iodine also. Iodine gets oxidized to iodic acid, HiO3. Now here again first reaction remains same, that is HNO2 HNO3 giving rise to H2O plus 2NO2 plus nascent oxygen. Then comes iodine plus oxygen plus water giving rise to 2, it is HiO3. So balancing this, again you require 5 oxygens here because you require your 5 oxygen atoms here. So multiply once again this with 5. Adding, we'll get here I2 plus will be 10 HNO3 giving rise to 10 NO2 plus 2 HiO3 plus it is 4 H2O. Again 4 H2O we have here, that is these two are coming here, so 4 H2O. So here iodine is getting oxidized to HiO3. So non-metals are getting oxidized to corresponding oxyacids, then metals. It oxidizes metals to respective metal nitrates. The products depend upon concentration of the acid, temperature, as well as the nature of the metal used. Let us take with the concentrated HNO3. Normally the byproducts are NO2 only with HNO3 if it is concentrated. Again reactions remain same if it is concentrated HNO3. That is HNO3 giving rise to, it forms H2O plus 2NO2 plus nascent oxygen. Suppose if you take copper plus oxygen, it forms copper oxide and dissolves further in HNO3 here. Finally it forms copper nitrate. It forms copper nitrate and H2O. So this will be 2 here now. Both are being balanced here. Reaction will be copper plus 4 moles of HNO3. 4 moles because 2 and 2 here. HNO3 giving rise to copper nitrate plus 2 moles of NO2 plus 2 H2O we have. So metals are getting oxidized to metal nitrate plus byproducts are depending upon the concentration of the acid. Similarly, you can take zinc also. If you take zinc, same reaction if it is concentrated one. So zinc plus HNO3. I'm writing reaction directly here. It forms zinc nitrate plus NO2 plus H2O. We balance this, we get here 4 HNO3 and this will be 2, this will be also 2. So it forms NO2 and then zinc nitrate is being formed. Then comes dilute one. If you take dilute HNO3, it depends upon the nature of metal used. The byproducts depends upon nature of metal used. If you are using copper, you are going to get nitric oxide. So copper plus HNO3 giving rise to, it forms copper nitrate plus nitric oxide plus H2O. It's forming NO, it will dilute acid is being used there now. When you balance this, we get here 3 and 8 here. This will be 3 here and 2, 4 here now. Then if you are using zinc, product is going to be different. With same HNO3 dilute acid giving rise, it forms zinc nitrate it forms, plus the compound is nitrous oxide plus product is water. To balance this, it comes out to be 4 here, then 10 here, then 4 here, then comes here 5. So this zinc is placed above hydrogen, the copper is placed below hydrogen electrochemical series now. So copper is giving NO with the dilute HNO3, zinc is giving N2O with dilute HNO3. So with dilute HNO3, nature of the product is depending upon the nature of the material which is being used there now. Next one, uses of brown ring test. One of the uses you can say. Brown ring test. The nitrate ions are detected by brown ring test. The nitrate salts have nitrate ion in that. We can do brown ring test for that. The nitrate salt solution is added to freshly prepared ferrous sulfate solution. So they take a test tube. It should be inclined position. So test tube is taken. It should be in inclined position there. And then they will be adding nitrate solution first. For this, they are going to add freshly prepared ferrous sulfate solution. Is added there now. I think you have done in the first year practicals. And then they will be adding along the walls of the test tube sulfuric acid here. That goes there now. And we can see between junction of two layers, we can see a brown color being formed now. Itself is called brown ring test. So you are taking nitrate salt solution, adding freshly prepared ferrous sulfate to that, and then adding sulfuric acid along the walls of the test tube. We can see a brown color between the junction of two layers. And if you see the formula of the brown color is, it is nothing but nitroso-ferrous sulfate is called the brown ring. So there, the NO3 minus the nitrate ions which are there, they are changing into NO in the process. The nitrate ion is being reduced to NO. NO forms a complex with iron plus 2 present in that. It forms nitroso-ferrous sulfate here, which is a brown in color. The brown ring test to identify the nitrate salts. Then comes, what are the uses of nitric acid here? Mainly used in the manufacturing of nitrogen fertilizer like ammonium nitrate. It is used as a nitrating mixture along with the concentrated sulfuric acid, the nitration of organic compound. So nitration mixture mainly contains HNO3 and sulfuric acid. It is used in the nitration process of many organic compounds. Used in the preparation of explosive compounds such as nitroglycerin, TNT, trinitrotoluene. They are explosive compounds. And used as an oxidizer in the rocket fuel. So it is used in the preparation of fertilizers like ammonium nitrate in the nitration mixture of HNO3, and then you have sulfuric acid, preparation of explosive compounds like nitroglycerin and TNT used as an oxidizer in the rocket fuel. So finally, what you have learned today? We have learned the oxides of nitrogen, their structures, their preparations, as well as preparation of ammonia, preparation and properties of HNO3 we have seen.